Hello everyone, welcome to the CO2 Gas Absorption Lab. My name is Emmanuel, I'm the TA for this course. So pretty much for the CO2 Gas Absorption Lab, it's a system whereby we have a custom built gas absorption column, and the idea is to absorb CO2 into water in a packed column. Like you can see, the packings of the column is made of flexiglass, so it's more of an industry standard packings. This is the CO2 gas tank. This is the source of our CO2, obviously. And you have the air that comes from the building. So the CO2 get mixed with the air, and these are the mass flow meters that helps capture the amount of CO2 that goes into the system. This is the lab view interface that pretty much captures all the different parameters that are involved in this CO2 gas absorption lab. You have the temperature readings that gives the temperature of the different streams at different points in the column or in the line. You have the pH, which gives the pH of the exiting water stream at the base of the column. You have the concentration of CO2, which gives the amount of CO2 that is leaving the column at the top. You have the mass flow that tells us the amount of water that we are sending into the column. And we also have the amount of CO2 and air that is being sent together as the gas mixture. Then you also have the pressure P1 and P2, P1 being the pressure at the top of the column, and you have pressure P2 being the pressure at the base of the column. And this simply just gives the total mass of gas stream into the column. And then the changes in these variables are captured with the use of this plot. You have the one that captures the temperatures that lets us know if we have reached steady state, and then the results can be recorded for the different conditions. By the way, there will be 3 different conditions in this lab: condition 1, condition 2, and condition 3. And the amount of CO2 and air is captured with the use of these mass flow meters. This is for CO2 and this is for air. Then this gas stream goes and comes to the bottom of the column and rises up by virtue of the differential pressure that exists within the column, P1 and P2. P2 being the higher pressure and P1 being a lower pressure. And then you have the water stream that comes into the column from the top, is pumped to the top of the column, and the temperature of this inlet water is measured by thermocouple 2 and is read off in the lab view as T2. And then you have thermocouple 3 that measures the temperature of the exiting liquid stream from the column, which is a mixture of the absorbed CO2 and the liquid water. And you also have thermocouple 4, thermocouple 5, and 6. These are different sensors at some section in the column that gives a measure of the temperature at different sections. Right here is the pH compartment. It pretty much measures the pH of the exiting effluent from the base of the column. We are going to start the experiment right now for condition 1, which is to give a certain amount of desired flow of air, CO2, and water into our system. And condition 1 is such that the amount of CO2 is 0.3 standard liters per minute. I'll give that value. The amount of initial flow of air is 2.2 standard liters per minute. I give that value. And I will start the process. First, we'll start the process with the gas flowing into the system, and then afterwards, we will run for the amount of water we want to go also into the system. As you can see, we can already observe different transients in the system, especially temperature T4 within the column and T5. The expectation is that they'll be quite close to each other. For a measure of the temperature of the column, we take pretty much the average of T4 and T5. And then we'll stop condition 1 and move over to condition 2. So we're just going to wait for the system to become steady, and then we will move on to the next condition, condition 2. So you can see the CO2 value is beginning to drop, be enough contact between the water that is trickling down the column and the rising CO2 air mixture. So this amount of CO2 at the exit of at the top of the column will continue to drop until we get to a steady state value. And at that steady state value, we will stop the experiment and go to the next condition, condition 2. There is expected amount of CO2 that can be emitted to the environment. So the government pretty much will give a particular standard that must be met. So this experiment gives an indication of how much of CO2 can be scrubbed in the system and how much will be released to the environment. Okay, so this value is going to continue to drop up until a certain value. So that value typically is expected to be less than the standard that you are permitted to emit to the environment. As you can see, the system is pretty much at steady condition. So we'll move to condition 2. So condition 2 is to increase the flow of CO2, to double the flow of CO2 and drop slightly the flow of air such that the total gas flow remains constant as 2.5 standard liters per minute. So I'm going to do that right now. So I'll increase the flow of the CO2 from 0.3 standard liters per minute to 0.6. Drop the flow of air from 2.2 to 1.9. Watch again and see as the different variables will once again change. We'll go into the transient stage, and with time, the system will become steady again, and that will conclude condition 2. So we change the flow of CO2 from 0.3 to 0.6 standard liters per minute, as you can see. And we change the flow of air, in this case, from 2.2 standard liters per minute to 1.9 standard liters per minute. And we kept the flow of water constant at 1.5 standard liters per minute. One thing that is important for you to notice is that in as much as you want to ensure you have enough liquid flow in your column to scrub as much CO2 as possible, or absorb as much CO2 as possible, you can see that the water is trickling down the column, but you don't have water going up directly into the column. You just have enough water at the base of the column, such that only the gas stream goes into the column, but not the exiting water flooding back up into the column. So you also want to avoid flooding of the system, because when that happens, obviously, the system will not work efficiently. All right, so as you can see, pretty much the system is steady. We've reached steady state. So and that brings us to the end of condition 3. So we can pretty much say we have reached steady state and the whole experiment is done. So I'm just going to stop this. I'm going to end this by stopping this. And once we end this, we have the results automatically recorded in an Excel sheet, okay? And this is exactly what we have. So all the data that has been captured from the beginning of the experiment all through to the very end is captured in this Excel sheet. And it tells us pretty much how long it took us to complete the experiment. So for column 1 is time, column 2, 3, 4, 5, 6, 7, those are the temperature conditions. Then column I is the flow of air. Let me double check that. So condition I is the flow of water into the system, and condition J is the flow of CO2 into the system, as you can see, 0.303305 and the rest of them. And column K is the flow of air in standard liters per minute, same as CO2, standard liters per minute, 2.2, and the rest of that. And then you have the P1, which is the pressure at the top of the column in PSI. You have P2, which is the pressure at the bottom of the column in PSI. And then you have the amount of CO2 at the exiting gas stream, which is in mole percent. So you don't need to do any conversion for this because the value is already in mole percent. And then you have the pH meter reading that gives you a measure of the amount of CO2 that's exiting the column at the base through the water. So the amount of CO2 that is absorbed in the effluent liquid. Each group will get different conditions, different condition 1, condition 2, condition 3. So you have a varied data, and you use this to solve the problems that have been posed for this CO2 gas absorption lab. And that's pretty much it.